Now let's put this whole idea into a three-dimensional picture so we can start thinking about the volume under graph of f of x, y, leaving the area question for area of the region, the question of the area of the region for just a little while. Okay, we'll come back to the idea of the total area, but what I'm about to say I think is clearer if we do it in the context of a volume. So we have here an x, a y, and a z-axis, and forgive the inconsistency of the direction of the x-axis. It's supposed to be straight, and I drew it from a bad perspective, I guess. So we have the curve, okay, and we could label this curve, wouldn't do any harm. This is the curve where x equals square root of y. Okay, and we're looking at 0 less than or equal to y less than or equal to 2. So that the region is this with 0 less than or equal to x less than or equal to the square root of y. So there's the curve, here's our region. And we've partitioned it in the way that we've just seen. Okay, well, let's explain this. Here's the way I drew the typical interval that started on this diagram here, just a typical xj minus 1 to xj, yi minus 1 to yi. There's the interval. Here's a little bigger picture of it. We see that x goes from xj minus 1 to xj, y goes from yi minus 1 to yi. In 3 dimensions, we could draw that region, and I've drawn it a little extra big here. I've drawn an interval representing the interval from yi minus 1 to yi, and from xj minus 1 to xj within the region. Okay, so this is within the region. We know that xj is effectively less than or equal to the square root of whatever y is here. Now we've got a range of y values, a range of x values. We'll see how we deal with that, but what I just said is pretty much the case. These regions run from some y value here out to the square root of that y value. Now what we're going to do is we're going to assume that there's some function f of x, y, and the graph of that function lies up here above the xy plane. To find the volume of the graph above just this rectangle, and this really is a big representation of what we're going to think of as a tiny rectangle. Okay, we take any old point in this region, and we're going to call the coordinate of that point y sub I star. And we take a point here, anywhere in the x interval, and call that x sub j star. Then we have within this rectangle the point xi star, xj star, xj star, I'm sorry, yi star. At that point, the function f of xy, and let's invoke that, volume under the z equals f of xy curve, and actually I don't want to find the volume. Yeah, I do. Okay, volume under the z equals f of xy curve above the region being the region we've defined down here, the region we've been talking about all along. Okay, Well, let's just find the volume above this little rectangle here. Okay, well, in order to find the volume, as we've seen with some examples that we've done, we could take this corner point and get a reasonable approximation to the volume. Okay, we could take the value of f of xy here, that would give us the altitude of this region, and we'd have a rectangular base that's delta y by delta x. Alternatively, we could take any point inside this region and get what might or might not be a better approximation. If we take a value here, so let's just say that our value of the function is represented by this. So this here projected back to the axis gives us an equal interval here, and this displacement here from the origin up to here is f of xj star yi star. So that's the length of this, and we can then construct, looking for a good color here, we could construct the rectangle of this, the rectangular solid with this base having this height, and it would look something like this. Okay, so here's our solid. Here's a point on the top of this solid. It's a rectangular solid, and what's its volume? Okay, the volume of this thing is the delta x j, making sure I've got my subscripts right because I'm still kind of struggling with these reverse subscripts. And then that's going to be times f of xj star yi star. Okay. Delta x here, delta y here, f of xj star yi star. And I'm using colors here. So I can kind of color code these things. The delta y is just the length of this thing, so I'll just kind of put a green circle around that to match the green. The delta xj is the length of this side, so I'll just put a red circle around that. And the f of xj star yi star is the altitude of this figure, corresponding to the length of this purple line. And there's our volume. Okay. Now, we're going to do a limiting process as you did in first year calculus. We're going to let the delta x's approach 0. We're going to let the delta y's approach 0. And as the delta x's and delta y's approach 0, every point of this rectangle is going to be much closer with each approach than together. Every point is going to be much closer to every other point than, well, every point in this rectangular region is going to become closer and closer and closer together, which means that the error you get in using a height at any old value within the rectangle becomes insignificant. Now that's provable. That can be written in symbols, but the intuitive idea should be clear. And if you think back to the question I asked about the block somewhat earlier, taking a 4x5 area and calculating the altitude and so forth based on that and the possible error that you get, the percent error gets much smaller as the rectangle gets much smaller. Okay. I'm not sure I said that very well, but make sure we understand what this picture is telling us. This rectangle corresponds to this rectangle or this rectangle, and this is any old point in the rectangle. We use any old point as a basis for calculating the volume using the function value at that point as the altitude above the base. And this is what we get. So what's our expression now for the total volume? Okay, the total volume of our rectangular approximations is what? Well, by analogy with what we have here, it's going to be the sum from I equals 1 to, make sure I've got my letters right too, because I keep wanting to reverse them, to n of the sum from j equals 1 to m of delta xj, delta yi, f of xi star, xj star, yi star. It's just the sum of all these, and I did something really wrong here, and I've got to fix that. I factored out the delta yi here, but I can't factor out the f of xj star, yi star. The yi's are the same for all your j's. Okay, they're the same all the way across the strip. You have the same width all the way across. The values of f clearly change. So I'm going to want to correct that by just putting my final parenthesis here. So I haven't factored anything out of this sum. Okay, so this sum represents the sum of all such, the volumes of all such regions from here to here within this strip. Now, I can factor the delta y sub I out of whatever happens within this strip. It's common for given value of I, make that j look more like a j, it's common for every value of I to all the terms in this sum. So I can write this as the sum of x, f of xj star, yi star, delta xj, but factor out the delta y sub I. So now I have every strip is represented by a sum in the parentheses here, and then I sum over all strips. So we'll continue with this.